Okay, so when starting to study organic chemistry, you have to understand that organic chemistry is basically the study of how carbon and hydrogen bond with other chemical compounds, notably nitrogen and phosphorus, and basically only a few other atoms or elements that we come into contact with. So basically, you have to understand that organic chemistry studies hydrocarbons and how they bond. It's the study of carbon, pretty much. And so in order to understand organic chemistry, we have to understand how carbon likes to bond. Basically, any atom or any element that's trying to bond is going to have what you call valence electrons. And what we mean by valence is basically that electrons, and I'm going to draw a hypothetical carbon here in red, electrons generally stay in different energy levels around its parent atom. So what I mean by that is that usually with carbon, well, actually not usually, always, but in carbon you're always going to have 6 electrons, and these electrons like to habit certain energy levels around the atom, and they don't like to jump out of these energy levels. They like to stay where they are. And so the first energy level is always going to have to hold 2 electrons. So if we draw this circle around this carbon representing the first energy level, and these are things that you don't have to know. I mean, you would learn this in inorganic chemistry. So this has nothing to do specifically with organic chemistry, but it's something that you need to understand so that you understand how carbon bonds. So in our first energy level, and let me just switch my color to blue here. In the first energy level, there's always the first 2 electrons of carbon. So let's draw those in blue right here. In the second energy level, there's always going to be, and I'm going to draw the second one in red again, there's always going to be the last 4 of carbon's electrons, because remember, carbon always has 6 electrons. That never changes. So we have to distribute these electrons into their respective energy levels. The first energy level only holds 2. The second can hold up to 6, I believe. So we draw carbon's last 4 electrons, 1, 2, 3, 4, in the second energy level. Alright, and that's basically all there is to it with carbon's valence electrons. These 4 outer electrons are going to be the electrons involved in bonding with other atoms. Another way you have to look at it is that chemical bonds always involve an electron transfer of some sort. Most chemical bonds only involve just 2 electrons bonding together from 2 different atoms. So if we had a hydrogen coming here, hydrogen only has 1 valence electron, and you learn all of this stuff in organic chemistry about valence electrons and how much each notable element has available for bonding in its valence shell. So hydrogen has only 1 because it only has 1 electron available to it. So hydrogen will always have only 1 valence electron. And if this carbon wants to bond with this hydrogen, then this hydrogen will interact with carbon's valence electron and its valence electron, forming a hydrogen bond. And that's basically it. This is how carbon bonds using its valence electron. Everything bonds using its valence electron. And basically, if you understand that, you understand that carbon always, since it only has 4 valence electrons, will have 4 bonds. Notable exceptions, and in organic chemistry, there's an exception to absolutely everything. That's the first thing that you should understand about that. So moving on, carbon will always want 4 bonds, without exception. It's happy when it has 4 bonds. So since we now know that carbon always likes 4 bonds, how do we start making chemical compounds involving carbon? Well, let's bring 4 hydrogens over here into the mix, and we're going to see how, for example, the compound methane is formed. And later in later videos, I'm going to teach you exactly how to name these, how to name something like methane or ethane or propane or butane, so on and so forth. But basically, what's going to happen is a pretty simple process. The hydrogen here is going to interact with the valence shell electron of this carbon forming a chemical bond. Remember, chemical bonds always involve two valence electrons, and when two valence electrons come together, a bond is generally formed. This hydrogen is going to do the same thing here. This hydrogen is going to do the same thing here. This hydrogen is going to do the same thing here. And so now you have chemical bonds surrounding each valence electron of a carbon atom, and this makes up the molecule methane. It should be noted that these don't have to be hydrogens over here. This can be, I'm going to take away one of the hydrogens bonded to carbon's valence electrons, and I'm going to add another carbon. Carbon also has 4 valence electrons like I've just drawn. So these valence electrons can bond with this carbon, forming a chemical bond. This valence electron and this valence electron forms another bond to carbon this time. Alright, and these are how hydrocarbons are formed. And so the convention, when you see a carbon bonded to another carbon, is that we draw it with the hydrogens implied. And what do I mean by that? I mean that if we drew a molecule like this, 1, 2, 3, each point counts as a carbon. Alright, so we have 1, 2, 3, 4, 5, 6 carbons. If we drew a molecule like that, then what is implied? Well, each point is a carbon, so we'll draw a carbon here, carbon here, carbon here, carbon here, carbon here, and a carbon here. What else is implied? Well, carbon always wants 4 bonds. So this carbon, for example, this carbon right here has is bonded to another carbon to its right and another carbon to its left. What does that tell you? That 2 of its valence electrons still haven't bonded yet. But with chemical compounds, we understand that since carbon always wants 4 bonds due to its 4 valence electrons, that there has to be hydrogens here. So whenever you see a carbon, count how many of its valence electrons are satisfied, and you can understand, and the ones that aren't, you can pretty much fill them in as implied hydrogens. The hydrogens are there, the convention is just not to draw them. So this carbon would have, since it's bonded to only one other carbon here, this carbon here is bonded to only one other carbon here, so that must mean that 3 of its valence electrons are not satisfied, so that means that this carbon would have 3 hydrogens attached to it. This carbon would have 2 hydrogens attached to it. This carbon also would have 2 hydrogens attached to it. So would this carbon, so would this carbon, so would this carbon, so would this carbon, and this one, once again, would have 3 hydrogens attached to it. And that is how we, whenever you see these pill bottles or whatever with these chemical compounds on it, and you see a line structure or something like this, and then maybe, you'd have, and we're going to get into this later, a cyclic compound with double bonds around it. Whenever you see like a chemical compound like that, you have to first look at it understanding that there are going to be a bunch of implied carbons, and I'm going to show you another example of these kind of compounds with cyclic and non-cyclic examples. And when I say cyclic, I just mean that the compound is in a cycling fashion. For example, this is the molecule for trinitrotoluene, or TNT. As you can see, the compound has bonded to itself, so to speak, in a cyclic fashion. And so if we look at another molecule here, and this is capsaicin, the molecule that makes your Tabasco sauce spicy, or your jalapenos spicy, or whatever spicy food you decide to eat. And so in this case, we see a straight chain where the carbons are in their default straight chain configuration, and we also have a cyclic portion of this compound too. And so I'm going to go into more detail as far as how straight chain compounds are named and identified. If we take a compound here like this, and we see this drawn on I don't know, a medicine bottle information sheet, we're just seeing a bunch of zigzag lines. It doesn't really mean much. But like I've showed you before, each one of these points represent a carbon, and each of these carbon have 4 valence electrons and need and therefore those valence electrons need to be fulfilled. So in this case right here, this carbon would have 3 hydrogens coming off of it, and any terminal carbon, you know, and what I mean by terminal meaning it's finishing off the compound, like this carbon right here, is always going to have 3 hydrogens. Now any carbon, and we call these secondary carbons, these are called secondary carbons, these carbons right here, and this one, and this one, and this one, all of these are secondary carbons, and the reason we call them that, of course, is because they're bonded to 2 other carbons. This carbon here is bonded to this carbon here and this carbon here. Alright? So these are secondary carbons, and secondary carbons always, since 2 of their valence electrons are already accounted for in the 2 carbons that it's bonded to, secondary carbons always have 2 hydrogens implied. And so what this would look like in the 3D structure of the molecule is we would have something like this, where the hydrogens would be in 3D space arranged in a way so that one hydrogen, this hydrogen here, is coming out of the plane of the paper. Again, you're visualizing this in 3D right now. One hydrogen is coming out of the plane of the paper towards you, and then another hydrogen, this hydrogen right here, is going away from you, out of the plane of the paper. And so this is how we kind of draw these things in a 3D fashion on a 2D piece of paper. Alright, so with that said, let me get rid of all this stuff here. With that said, we're going to draw the rest of the hydrogens out just so you kind of get a feel for how the molecule really looks when we draw this out here. And so you know all of this is implied, but this is how the molecule actually appears instead of just drawing the zigzag lines. Alright, so it shows all of these hydrogens out here in 3D, and so then you have the final terminal carbon here with its 3 hydrogens attached. And so this is how this molecule actually looks in 3D space. And if you compare it to the actual 3D ball and spoke picture of this molecule here, what you'll see is, with the white balls representing hydrogens and the black ones representing carbons, you will see that this molecule actually measures up to what I just drew right here. This molecule resembles what I just drew right here. So just for a quick recap, last example we showed you the compound methane, which is just carbon bonded to 4 other hydrogens.